If you turn this video at one point off, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I am trying to learn biochemistry today, covalent bonds, and after we've done that, we're going to do shoulder impingement training. And if you participate in the shoulder impingement training, then it's relatively obvious. Covalent bonds. When a covalent bond forms, neither of the combining atoms loses or gains electrons. Instead, the atoms form a molecule by sharing one, 2 or 3 pairs of their valence electrons. Okay, so that is the big thing. We don't lose an electron giving it to someone else or something. They are using it as the same one double. The electrons in each pair are said to be shared because both spend most of their time in the region between the nuclei of the two atoms. The electrons in each pair are said to be shared because both spend most of their time in the region between the nuclei of the two atoms. Okay. So that seems people can look at that with a very good atomic telescope, whatever, microscope, and then they can see with one electron or the one how many covalent bonds it has is all the time between the two. And so they say they are shared. Unlike ionic bonds, covalent bonds can form between atoms of the same element as well as between atoms of different elements. I think that ionic bonds can form only with elements of other elements. No, it is logic. It makes more sense to say the other way around. Ionic bonds can form only with other atoms of the same type, and covalent bonds can form with one of themselves, but also with other ones. Covalent bonds are the most common chemical bonds in the body, and the compounds that result from them form most of the body's structure. Okay, so it's a very big thing. Most of the human body consists out of covalent bonds. What's the most common chemical bond in the human body? And with 2 atoms, it can be of the same type, but also with another type, bound together through sharing an electron. No one of them loses an electron in the process of bonding. It is easiest to understand the nature of covalent bonds by considering those that form between atoms of the same element. As noted, covalently bonded atoms may share up to 3 electron pairs. As noted, covalent bonded atoms may share up to 3 electron pairs. A single covalent bond results when 2 atoms share 1 electron pair. For example, a molecule of hydrogen forms when 2 hydrogen atoms share their single valence electrons. Why do we use that example? Why should it be a hydrogen molecule? A hydrogen molecule consists out of hydrogen and becomes a hydrogen through having a covalent bond. So it's just hydrogen and hydrogen, and there could be 2 hydrogen, just a million hydrogen, but as soon as they share 1 electron, they are a hydrogen molecule. Is it that? I think that is it. That's it. For example, yeah. And that allows then the hydrogen molecule to have a full valence shell at least part of the time. A molecule of hydrogen forms when 2 hydrogen atoms share their single valence electrons, which allows both atoms to have a full valence shell at least part of the time. What is the problem? Don't they have always a full one? Do we want to, but hydrogen doesn't want to? Is it then H plus or something? Maybe we're coming into that. But here we're having a little rough. We're having hydrogen with 1 electron and hydrogen with 1 electron, and together now they have 2. Do we want to? A double covalent bond results when two atoms share two pairs of electrons, as it is the case in the oxygen molecule. A triple covalent bond occurs when two atoms share three pairs of electrons, as in a molecule of nitrogen. That is the third example. Notice in the structural formulas for covalently bonded molecules in this figure that the number of lines between the chemical symbols for two atoms indicate whether the bond is a single with one line, double with two, or triple with three lines covalent bond. Here the N3, O2 and H1. It's still N2 and O2 and H2, so it doesn't change anything. It's now just two nitrogen. Why don't we have anything just through having more electrons in the shells? The same principles of covalent bonding that apply to atoms of the same element also apply to covalent bonds between atoms of different elements. Okay, same principles. Methane, CH4, a gas, contains covalent bonds formed between the atoms of two different elements. The valence shell of a carbon atom can hold 8 electrons, but has only 4 of its own. That is what we mean. Okay, I have a little theory. The shells can hold so much electrons, but they don't always have so much. Hydrogen has one shell, and on the first shell, it's fixed, there can be 2 electrons. Hydrogen has just one. And now if it couples up with another one, it has a 2, and now it has a full shell. Carbon has 2 shells here. On the first shells, there can be p to the 2, and the shell is full. But on the second shell, technically, there could be 8 electrons. And carbon has just 4 there. It has 2 on the inner and 4 there, so 6. But there are still place for 4, and if now someone comes in, then it is 8. That is not my theory. The single electron shell of a hydrogen atom can hold 2 electrons, but each hydrogen atom has only one of its own. A methane molecule is the product of 4 separate single covalent bonds. Each hydrogen atom shares 1 pair of electrons with a carbon atom. Let's see. Each hydrogen atom, these 4 H's, H, the letter H here, atom shares 1 pair of electrons with a carbon atom. And now we're having CH4. We're having 1 carbon and 4 hydrogen, CH4. We're having carbon in the middle. It has 6 electrons. 2 are on the first shell is full. There are still 4 electrons left. Carbon has 6. 4 are on the second shell, but the second shell has room for 8. And now coming 4, 1 in, and now it has the 4, 1 of itself, and 4, 1, and the hydrogen has place for 2, and that is why hydrogen and carbon can bond together, because hydrogen has room for 1 more, and 4 of them can now come together. And now we're having CH4, 1 carbon and 4 hydrogen, and that is methane. In some covalent bonds, 2 atoms share the electrons equally. One atom does not eject the shared electrons more strongly than the other atom. This type of bond is a non-polar covalent bond. The bonds between 2 identical atoms are always non-polar covalent bonds. So that if it is between 2 atoms of the same type, it is non-polar always. And the non-polar type is when these atoms don't eject the electrons more stronger one than the other. I think that the one which has more electrons is the one attracting the other one, at least from all these graphs here. Another example of a non-polar covalent bond is the single covalent bond that forms between carbon and each atom of hydrogen in a methane molecule. Another example of a non-polar covalent bond is the single covalent bond that forms between carbon and each atom of hydrogen that was right here in the final molecule. In a polar covalent bond, the sharing of electrons between two atoms is unequal. One atom attracts the shared electron more strongly than the other. When polar covalent bonds form, the resulting molecule has a partial negatively charged near the atom that attacks electrons more strongly. Okay, because one has an electron away to something in a polar bond between two different atoms. And one of these atoms attracts the other electron with shared electron more. One atom attracts the shared electron more strongly. And when polar covalent bonds form, the resulting molecule has a partial negatively charge near the atom that attacks electrons more strongly. The one which is attracting the shared electron a bit more to it is logically a little more negative. Two people are sharing something, and one person which puts it a bit more to it is not strong with it affected. And therefore the electron which is pulling in this shared electron a bit stronger than the other one is a bit more negative than the other one. At least one other atom in the molecule then will have a partial positive charge, and the other one is a bit less. It's a bit more positive because this electron doesn't make it a full -1 because it's a little bit out of the other side. It just gets half of the dose. Or whatever it is. This partial charge also indicates by a lowercase Greek delta with a minus or plus sign. And it's like it's 1 or whatever. With a minus and a plus. The most important example of a polar covalent bond in living systems is the bond between oxygen and hydrogen in the molecule of water. Later in the chapter, we will see how polar covalent bonds allow water to dissolve many molecules that are important to life. Okay. The basic things that we were saying here about that two things can come together. If it's of the same atom, it is non-polar. If it is, then polar. And one of these atoms pulls stronger at the electron. I guess the one which has more electrons in the first place. It's pulling it, or the other one is a bit more positive, the other one a bit more negative. Signified with a delta sign, that is just 1 or whatever, in Greek letter, with plus and minus. And on the first shell can be 2 atoms, on the second shell 8, and therefore carbon, which has 6 to the first form, the other one, can form up with 4 other hydrogen, which have just 1 electron. And now we can share all this 1 electron with one on the carbon thing or whatever, and that gives now CH4, so 1 carbon and 4 hydrogen at the outside, methane. And 2 hydrogen can also come together. Each one has just 1 electron on the shell, but there's place for 2, and now we can share and have 2 together. That was the biochemistry part. If you were here for biochemistry, you can go direct to the next part of biochemistry. If you stay here and participate in the short engagement training, then it's very important. We're having a good stable stance, and we're doing shoulder circles. If you participate in this very important, back with the shoulders up, in front, and down, back, up, in front, and down. And again in front, up, back, down, front, up, back, down. Long arms with strong fists, go as far back as you can. High up, and front, and down, back, and front, and down. Up, back, down, front, up, back, down. Now, long arms, strong fists, shoulders down into the rib cage and together. Turn the arms to the inside. Arms to the outside, shoulders down and together. Arms inside, shoulders down and together. Arms outside, shoulders down and together. Arms to the sides, a bit in front, arms in front, shoulders down and together. And back. Arms back, shoulders up and in front. Arms in front, shoulders down and together. Arms back, shoulders up and in front. One arm in front, Shoulder back and down, pull the arm and have flat fingers, try to relax the arm, go with back, right shoulder, turn the palm to the sky. The other. Shoulder back and down, pull the arm and have flat fingers, try to relax the arm, go with back with the shoulder, turn the palm to the sky. That was the short impingement training. Thank you very much, and at the next time.